In the realm of machine learning, few-shot learning, FSL, has garnered significant attention for its ability to rapidly generalize deep networks to new tasks with only a few annotated examples. However, most current FSL approaches focus on 2D image domains, with the implication in 3D perception being relatively underexplored. This work delves into the challenges and opportunities of 3D few-shot learning, 3D FSL, which is more challenging due to unordered structures, high intra-class variances, and subtle interclass differences. The authors conduct a systematic study of recent 2D FSL and 3D backbone networks for benchmarking few-shot point cloud classification. They propose a strong baseline and learning architectures for 3D FSL, as well as a novel plug-and-play component called the Cross-Instance Adaptation (CIA) module to address the high intra-class variances and subtle interclass differences issues. The CIA module consists of two modules: self-channel interaction, SI, and cross-instance fusion, SIF, which can be flexibly inserted into most current FSL algorithms with few changes and achieve significant performance improvement. The authors also introduce new splits of ModelNet and ShapeNet core, constructing two benchmark datasets, ModelNet40-FS and ShapeNet70-FS, for 3D few-shot point cloud classification. They identify challenges in 3D FSL, including strong intra-class variations and subtle interclass differences among the support set and query set, and propose the CIA module to learn more discriminative representations. The proposed method achieves state-of-the-art performance on the two newly built 3D FSL benchmark datasets, ModelNet40-FS and ShapeNet70-FS, under different settings. The contributions of this work include the first systematic study of 3D few-shot learning, proposing a strong baseline for 3D FSL, and introducing a novel plug-and-play cross-instance adaptation (CIA) module for 3D FSL. This research proposes a novel framework for 3D few-shot point cloud classification, addressing the challenges of subtle interclass differences and high intraclass variances. The framework consists of three modules: self-channel interaction, SI, cross-instance fusion, SIF, and cross-instance adaptation, CIA. The SI module models channel-wise relationships to learn more diverse features, while the SIF module explores instance-wise interaction to address high intraclass variances. The CIA module combines the SI and SIF modules to learn more discriminative and diverse features. The framework is trained end-to-end by minimizing the cross-entropy loss, and the authors evaluate its effectiveness by comparing it with state-of-the-art few-shot learning algorithms on two 3D point cloud classification datasets. The results demonstrate the superiority of the proposed framework in addressing the challenges of 3D few-shot point cloud classification. The study also introduces a strong baseline using ProtoNet with DGCNN and a novel CIA module, which achieves significant performance improvement with different FSL algorithms and can be adapted well into different backbones. The authors construct two benchmarks, ModelNet40-FS and ShapeNet70-FS, for 3D point cloud classification, ensuring that the training and testing sets are disjunctive. Experimental results show that the proposed CIA module achieves significant performance improvement, and the ablation study demonstrates that both the SI and SIF modules contribute positively to the performance of ProtoNet on ModelNet40-FS and ShapeNet70-FS. The network incorporating the SIF module achieves about 3% improvement for the one-shot setting. Comparisons with other 3D FSL methods indicate that the proposed baseline achieves much higher performance on both benchmarks. The comprehensive review of 3D point cloud processing literature focuses on deep learning-based methods for classification, segmentation, and object recognition, covering a wide range of topics including few-shot learning, metalearning, graph neural networks, and CNNs. References drawn from prominent researchers such as Charles R. Chi, Hao Su, and Leonidas J. Guibas emphasize the importance of data augmentation, transfer learning, and domain adaptation for improving performance. Few-shot learning is also addressed, where models are trained to recognize objects from limited examples, leveraging prototypical networks, relation networks, and metalearning approaches. Graph neural networks are shown to capture local and global geometric structures, referencing papers on Point GNN, SplatNet, and other graph-based architectures that achieved state-of-the-art performance on various 3D point cloud benchmarks. In the supplementary material, additional details on 3D backbone architectures, few-shot learning baselines, and the channel interaction module and cross-instance fusion module are provided. 3 types of state-of-the-art 3D networks are employed as support backbones: pointwise MLP networks, PointNet and PointNet++, convolution networks, PointCNN, RSCNN, and dense point, and graph-based network, DGCNN with edge convolayers. Few-shot learning baselines, including metric-based methods, ProtoNet, RelationNet, and FSLGNN, and optimization-based methods, MetaLearner and MAML, are discussed. The channel interaction module enhances input point cloud representation using 2 linear embedding functions to generate query and key vectors, and computes a channel relation score map. The cross-instance fusion module addresses low data and high intra-class variances issues in few-shot point cloud classification, updating prototype features by fusing them with query features using a MetaLearner. Additional experimental results demonstrate fine-grained few-shot classification, ablation studies of residual design in the Psi module, and the effects of CIA for 2D-FSL. The authors conduct an ablation study on the effects of cross-instance fusion, CIF, and spatial channel interaction, Psi, modules in few-shot learning on point cloud classification tasks, demonstrating that the CIF module improves the performance of the ProtoNet model, especially in the one-shot setting. The Psi module is shown to pay more attention to discriminative fine-grained parts of different classes. Experiments on the ModelNet40-FS and ShapeNet70-FS datasets validate the effectiveness of the proposed method in few-shot learning on point cloud classification tasks. The authors visualize the feature heat map of point cloud instances to qualitatively evaluate the proposed modules, revealing that the Psi module pays more attention to discriminative parts and structures. The paper provides a dataset split for ModelNet40-FS and ShapeNet70-FS, including the number of classes, instances, and categories. The authors introduce a novel module called Contextual Instance Attention, CIA, to enhance the performance of point cloud classification models. The CIA module is designed to improve feature extraction capabilities, particularly in scenarios with partial occlusion or varying scales. Experiments on various point cloud datasets demonstrate the effectiveness of the CIA module, with comparisons between the baseline ProtoNet model and its variants incorporating the CIA module. Heat map visualizations in figures 10 and 11 illustrate the enhanced feature extraction capabilities of the CIA module, showcasing its ability to identify and emphasize relevant features within each point cloud instance. The CIA module addresses limitations of existing point cloud classification models, such as handling partial occlusion and scale variations, by leveraging contextual information from neighboring points. The comprehensive evaluation and visualization highlight the potential of this approach in addressing challenges associated with point cloud data. The proposed confidence-aware initialization (CIA) module is integrated into the ProtoNet architecture to enhance its performance on point cloud classification tasks. Figure 12 presents a heat map analysis of the feature response regions of both ProtoNet and ProtoNet with CIA, revealing that the addition of CIA leads to more prominent and concentrated feature response regions, particularly in areas with complex geometric structures. The CIA module is mathematically represented as theta_0 equals phi, x_0, x_i, w, where theta_0 denotes the initialized feature embeddings, phi is a learnable function, x_0 and x_i are the input points, and w are the learnable weights. This module incorporates spatial information of point clouds into the initialization process, hypothesized to improve the robustness and accuracy of ProtoNet. Experimental results validate this hypothesis, as the ProtoNet plus CIA model outperforms the standard ProtoNet on several benchmarks. Notably, the CIA module does not introduce significant additional computational overhead, as demonstrated by the minimal increase in flops. The heatmap analysis also reveals that the ProtoNet plus CIA model exhibits more discriminative feature representations, attributed to the improved initialization scheme provided by the CIA module. The incorporation of the CIA module into ProtoNet leads to improved performance and more robust feature representations. The results suggest that the CIA module effectively leverages spatial information to enhance the initialization process, resulting in more accurate and robust feature embeddings. This improvement is achieved without significant additional computational overhead, making the ProtoNet plus CIA model a competitive approach for point cloud classification tasks.